Hi, so this is a presentation on solar panels and their properties and their manufacturing processes. So a little bit about me. My name is Keya Gupta. My mentor was Lee, and I'm from Seattle, Washington. So I chose this topic. I chose to do a presentation about solar panels specifically because, obviously today global warming is a huge issue. Um, and, electric power contributes a lot to that. So in 2021, the US greenhouse gas emissions, about 25% of the US's greenhouse gas emissions came from the electric power industry. And 24.3% of those emissions were fossil fuel combustions, which so all of this is equivalent to about 1,540.9 million metric tons of CO2 from fossil fuels for the electric power industry. Um, and the one really cool thing about solar panels is that they don't take fossil fuels. They use the sun and then they convert the sun's energy into electricity. Um, the process that we'll talk about on a further slide. So this entire process itself is pretty fascinating, and I am a big technology fan. Um, so yeah. So a little bit of context about the physics behind solar panels. So solar panels use semiconductors. And what a semiconductor, so I'm going to contrast a semiconductor with insulators and conductors, just to get a better understanding. So basically, the thing that differentiates semiconductors, insulators, and conductors is how easily, they can conduct electrons inside of them. So how easily can electrons move inside of the material? So with um, so when you have an atom, you have different the electrons of an atom can only exist in different discrete intervals called energy levels. And the and in conductors, you know, and so the outermost energy levels is called the valence band and the conduction band. Um, and so the valence band is just, the band with the outermost band. So in conductors, the valence band and the conduction band overlap. So, you know, electrons are free to go as they please. In insulators, the valence band and conduction band is super far apart. So you cannot excite an electron with enough energy that it can go from the valence band to the conduction band. So electrons are not free to move. But with semiconductors, the cool thing about semiconductors is that the valence band and the conduction band are close enough that the energy from one photon, the energy from a specific photon, can hit an electron, and the electron is then excited enough to jump from the valence band to the conduction band. Um, the other really important thing about so the other really important thing about solar panels is photovoltaic cells or solar cells. Photovoltaic is just a fancy word. So basically in a solar panel you have two different panels of semiconductors. You have an N-type semiconductor which has been doped and mixed with another material, um, so that it has more valence electrons. And then you have a P-type semiconductor which is mixed with another material to have less valence electrons. Um, and then you have an N-type, so then you have your N-type semiconductor, and then underneath that you have your P-type semiconductor. And so where they make contact is where they're kind of electrically, I guess, neutral. So that's called a p-n junction. So what ends up happening is that when a photon from the sun hits an electron in the N-type semiconductor, the electron crosses the band gap. So the electron jumps from the valence band to the conduction band and then is biased by the p-n junction to be collected. And so when you collect, so basically what ends up happening is that when you have a photon and the electron gets hit and it leaves that area of the atom, you then basically have kind of like a positive charge carrier because now there's no electron. So now, you have a positive area remaining, which also is biased by the p-n junction and gets influenced to be collected. There are So just a couple properties of solar panels. There's the efficiency of a solar panel, which is just a descriptive term. It describes how efficient a solar panel is. It's the percentage of solar energy shining on the panel over the amount of usable electricity made. That's typically determined in a lab. You have the band gap, which is just the distance between the valence and conduction band, which for semiconductors specifically should be between 1.1 and 1.7 electron volts. You have the life cycle. So this is pretty cool. So solar cells have a life cycle of around 25 years. It changes between solar cells. But after, they degrade, they become solid waste, which is why solar cells are not 100% clean. So in 2030, the US is actually expected to have around 1 million tons of solar panel solid waste. And beyond that, actually, solar panels can be toxic. They do use heavy metals in some solar panels. And so if the solar panel gets damaged at all, the heavy metals can leak into the environment. And also, once these solar panels have degraded and they become waste, they classifies it as hazardous waste and then they have to be disposed of accordingly. So it's really careful that we don't have toxic solar panels just because it's so easy for solar panels to get damaged. There's also something called temperature sensitivity or stability, which is also really cool. So basically, what ends up happening is that heat can causes semiconductors to fluctuate, and changes their properties. So, if a semiconductor is heated up enough, then you get a very little increase in the current of the electricity that it produces, but a huge decrease in the voltage that it produces, which obviously we don't want. We want a very temperature stable semiconductor and panel. And then lastly, we have radiation tolerance. So basically, over time, radiation hits the solar panels, and then the solar panels, the structure of the semiconductor gets messed up. And the band gaps of the semiconductor then get messed up, and then you know and then electrons and holes can recombine, which we don't want because then they're not carried, which we don't want because then they're not collected, and then we don't have electricity that we can use. So there are mainly 3 different types of solar panels. So there's the first generation of solar panels, which is the oldest generation. These are crystalline, these are older, they're much more standard in the industry, they're very expensive, and they're very reliable. You have second generation solar panels. They're cheaper than the first generation, but they're less efficient, but they're still pretty well developed. And then you have the third generation solar panels, which are still in testing. For the most part, they're very cheap, but they're not efficient. And they don't follow traditional solar cell technology, with the exception of multi-junction solar cells, which is basically a bunch of different types of solar cells stacked together, so that it can catch multiple different kinds of light. These are very expensive, but they primarily come in use in the solar cell in the aerospace industry. So further innovation in this field, third generation solar cells are still being developed. We have fourth generation solar cells, which are still in early lab development as well. It Fourth generation solar cells uses nanotechnology and nanostructures. But there's not a lot of research done on them because there's not a lot of development done on them. Beyond that, there's a couple common issues with solar panels is, they can't be in the sun for 24 hours of the day. This angle of the sun position, the time of day, the weather patterns, the altitude and location of the solar panel are all things that affects how much sunlight the solar panel actually gets and how much electricity can be made. So when uh, installing solar panels, you have to be very careful about where you install them so that they're actually useful. And solar panels do create waste. I mean, you have to manufacture them, and then, you also have to dispose of them after their lifetime. Um, but they are one of the cleanest sources of energy that we currently have, and they are also the fastest growing source of renewable energy today. And that's my presentation. Thank you.